Okay, recording and class. Okay, so if I am still talking at 2:45, can somebody please tap me on the shoulder? Just make sure we stop talking. All right. Last time we talked about Bose-Einstein condensation, and I went through it. The logic. Some of you asked me questions after class about the precise logic of how it works. I'm going to very quickly just remind you of how that worked. So what we discovered was that first of all, we proved that the chemical potential always had to be negative. Then we discovered that if we just simply calculate the constraint equation for the number of particles in the system, we found that the chemical potential went to zero, but it went to zero at a non-zero temperature, which I called Tc. And then the question arose, well, what happens afterwards? Because as you reduce the temperature, the chemical potential has to keep going up, but it can't because it has to be negative. And so what we realized was because of the epsilon to the 1/2 in the density of states in 3 dimensions in energy, what that meant was that the ground state of the system was not included in the integral, and so we add it explicitly as shown at the bottom of the left-hand panel. That is the occupation number of the ground state. And then what we wanted to see as well, as we're getting smaller and smaller, approaching the critical temperature, mu is getting much less negative. And so we can expand the exponential, and so we get that n0 is minus kt over mu. Now, the only way that we can resolve this paradox of how the mu can keep decreasing towards zero, but not go through zero and become positive, the only way we can do that is if we assume that mu itself is a number of order 1 over v, or equivalently, a number of order 1 over n. Remember that the density of the Bose gas is a constant. So being of order 1 over v is the same as order 1 over n. And so what that means is that there is a fixed fraction of the particles in the ground state, and as I take the thermodynamic limit, that fraction stays a constant. And so that's the point about Bose-Einstein condensation. It's not that there's a fixed number of particles in the ground state, it's that there is a fixed fraction. Now, how does that resolve the paradox? Well, what I showed you last time, but I didn't draw a very helpful graph, and I'm going to draw it for you now. So what happens then is that if I draw a temperature and I draw mu like that, so what is happening is mu is coming in like this, and then we get to, let's say this is critical temperature, and then after that, it continues to decrease towards absolute zero, but this number here, the thing that sets the scale here, is that mu is of order 1 over v, or equivalently 1 over n. So it stays a small number, a very small number, which gets arbitrarily small in the thermodynamic limit, but never goes to zero. And it only goes to zero at t is equal to tc, t is equal to zero. And so that is what I demonstrated for you by explicitly calculating the occupation of the excited states compared to the occupation of the ground state. And what we saw is that the occupation number of any state with wave number k is typically something, if I look at the particle density, that goes as volume to the minus 1/3 power. And so the occupation of any given state goes to zero, but the integral of them is non-zero. But for the ground state, the fraction of particles in the ground state is a fixed number as the system size goes to infinity. And that is what we mean by macroscopic occupation. So that's what is going on in this part here. Any other scaling of the chemical potential will mean that the occupation of the ground state will not be a fixed number, and therefore the total number of particles in the system, which is n0 plus n epsilon, that will not add up to a number that scales as n. And so it has to scale with n, and so that's the only way that we can resolve this paradox. So I invite you to think about that, and you'll get some more opportunities to think about it when you do homework 4. All right. So that's what we did last time. Now we're changing gears. So remember what we're doing in this part of the course. We're going through. We've now established the basic ideas of statistical mechanics. Now we're going through systems that are non-interacting, the systems that we can solve exactly, where the partition function factorizes, where we can solve it exactly. And so what we've done so far is particles bouncing around in the box, classical and quantum. Now we're going to look at spin systems. And after we've done spin systems, we're going to look at the harmonic oscillator and radiation. So we won't get to all of that today because it's a short lecture, but I'm going to get started now with the problem of the paramagnet. So the paramagnet is the spin equivalent of an ideal gas. So it's basically a bunch of non-interacting spins. As shown on the left panel, and they're in an external field. So the spins only interact with the external field, but not themselves. So the technical name for these things are dilute paramagnetic salts. They're dilute, meaning that they're not so close to each other that they interact by ferromagnetic or antiferromagnetic things. And examples of them, I'm going to just sort of write down the chemical formula for them, and we'll come back to this later when we do a real calculation. So let me just write them down though for you. So chromium, potassium, SO4, 2, and then 12 H2O. So that's one example. Here is another one, FeNH4, SO4, 2, 12 H2O. And here's another one, gadolinium, SO4, 2, 8 H2O. And these materials, they are in different quantum states, and I don't expect you to know the atomic physics of them, but I will just tell you what the quantum states are. So the paramagnetic ion in each of these is the following. It's a chromium 3+, it's iron 3+, and gadolinium 3+. And these ones here, the first two, they have, I think, the same quantum numbers. Yes, they do. So L equals 0, the orbital angular momentum is 0, and then the angular momentum, the spin angular momentum is J is S, is equal to 5/2 and 7/2 respectively. So the 5/2 one is the chromium, and the iron is the 7/2 one. Okay, and why it's like that, I don't know. Actually, I've said this completely wrong. I've got this wrong here. Let me try again. I always get this the long way around. So this is the iron and gadolinium. Okay, so these ones have L equals 0, and then the iron has J is equal to S is equal to 5/2, and for gadolinium J is equal to S is equal to 7/2, and then for chromium, this one has J is equal to 7/2, no, 3/2. Okay, and I tried to understand why that is the case, and I couldn't understand it. So I know it's true, but I can't tell you why. But that's chemistry for you, and I'm not a chemist, so there you go. All right, so let's think what we expect to happen. So now let's think about that. So these things are interacting with an external magnetic field. So the question is, we know that the free energy is U minus Ts. And so what do we expect to happen? As a function of temperature. Okay, so what we would expect is the following. Well, first of all, if I make the temperature go to 0, then the entropy part is not going to be very important. So it's all going to be determined by energy. So U then is going to dominate. And for that, if in this case, it means that the spins will lower their energy, their potential energy in the external field. Well, I'll write that down in a minute. In the external field H, which is in the Z direction. So I'll write that down. So that's what we expect for T going to 0. On the other hand, what do we expect for T going to infinity? Well, for T going to infinity, what we expect is then the entropy is going to be more important. So entropy will dominate. So when we say energy dominates, what we mean is that we can minimize the free energy by minimizing energy. And when we say S dominates, what we mean is that we can minimize the free energy by maximizing entropy. And why the difference there? Well, the difference is because we have this minus sign in the U minus TS. So that this is all what happens in all systems, not just these paramagnets. So if S dominates, then what that means is that means to higher entropy means more disorder. And so the spins are not aligned with the external field. So that's our qualitative picture then of what happens. So now that we've understood that, now let's do an honest calculation. So what I'm going to do is I'm going to start off by doing this classically. So we're going to start off with a classical case, and then I'll show you the quantum case. So let's start off by writing down the energy. So the energy of the system energy is just the Hamiltonian, is minus the sum from I equals 1 to n of mu I dotted with H. So mu is the magnetic moment. Of spin I, and so I can write this energy. This energy then is then just minus mu times the magnitude of the external field times the sum from I equals 1 to n cosine theta I. And let me draw for you the coordinate system I'm using here. So what I'm doing is this. I have the external magnetic field coming up the Z axis like so. So this is X, this is Y, and this is Z. Then I have the H H is going up here, like so. And then I have at the origin my particle, my spin. So it has a magnetic moment that is, say, pointing in this direction. So there is mu I. And then I can draw the polar angles. So this angle here is theta I. And if I project this down into the XY plane, like so. So then this angle here would be phi I, and that would be that's my coordinate system. So that's what I mean by cosine theta. So it just points like this, projected down onto the XY plane. And once I know the energy levels of the system, that's I get from doing classical mechanics. That's what I get from doing electromagnetism. That's what I get from doing quantum mechanics. Then once I've done that, then I have to do the statistical mechanics. So now we have to do the statistical mechanics. So this came from the electromagnetism. So now what is the partition function? Well, the partition function is as usual. It's given by trace of e to the minus beta h. So that is the general formula for the partition function for n systems. And when I mean trace, what I mean is the words sum over all degrees of freedom whatever they may be for the problem of interest. So I'm going to write this down schematically, and I'm going to actually do the integral for you directly. So in this particular case, the degrees of freedom are just the polar angles, theta I and phi I. Those are the things that change as the dipole moment changes its direction. So I'm going to write down what the trace means. I'm going to say that the trace is really the trace over the set of thetas and phis. And I'm going to think of that as being a sum over theta 1, phi 1, sum over theta 2, phi 2, and so on and so forth. And what I actually mean by sum, I will write it out for you explicitly in a minute, but we'll just use this notation just so that so we actually get to a point where we have to do a real calculation. So that is our formal way of writing it down. So now we know that the spins are non-interacting. And so what that means is that the partition function is going to factorize. And we can see that explicitly. So let's see how that happens. So I have Zn. It's a function of beta, the 1 over kt. It's a function of the external field. It's a function of the magnitude of the dipole moment mu. So it's something like this. And then it's going to be the product over all of these thetas and phis, which I'll write technically like that. And now let's write down what the energy is. So the energy is a sum of terms. So when I have an energy which is a sum of terms, when I write it in the partition function, it factorizes into a product of terms. So this is e to the beta mu h, and the sum from I equals 1 to n cosine theta I, and then this is then the sum over the thetas and the phis. And then I can write this exponential as the sum, as the product of the over I equals 1 to n of e to the beta mu h cosine theta I, like so. And then because this measure itself factorizes, as I have on the bottom of the left-hand panel, so then I can write this whole thing as then the product from I equals 1 to n of this thing, the sum over theta I, phi I, e to the beta mu h cosine theta I. So in here, so there's this outer sum, which is I. That I is in here, and in here, and here. And each of these things are you're summing over all possible values of the thetas and the phis. So this then is just a dummy variable in here. So this is then a dummy variable, because it's going to give you the same result for each value of I. By summing over whatever I call it, I just integrate over all possible values of theta and phi. Theta going from, you'll see in a minute, phi going from 0 to 2 pi, theta going from 0 to pi. So the value, so this thing inside here is independent of I. And so what that means is that the end result is that this thing is then going to be Z1 of beta mu h raised to the nth power. And here my Z1 is the partition function for one spin. And that is the sum over the values theta and phi for my one spin of e to the beta mu h cosine theta. So now I have to do that, I have to do for one spin. So of course, when we say the sum over the values, it's really an integral because those values go over a continuum. So in reality, this thing here is an integral. And as you can see, theta is between 0 is less than theta is less than pi, and 0 is less than phi is less than 2 pi. And so this whole thing is then just the following integral, z1 of beta mu and h is equal to the integral from 0 to 2 pi d phi, the integral from 0 to pi d theta. But what is the measure in spherical polar coordinates? The measure in spherical polar coordinates for the angular part is sine theta d phi. So there's a sine theta in here that comes in. And then I have the actual integrand itself, and the integrand itself is e to the beta mu h cosine theta. So let me just write that down. The integral over solid angle in spherical polars is sine theta, is sine theta d phi. So that's the measure, and that's what we've used. So now we can do those integrals, and so the integral d phi, since the integrand doesn't depend on phi, the integral d phi is just equal to a factor of 2 pi, so we don't really care too much about that. And then to calculate the rest of it, notice that it's very simple to calculate because z1 beta then is equal to 2 pi times the integral from 0 to pi d theta. And since we have that sine theta, we have a function times the derivative of its function. So we can write this whole integrand as d by d theta of e to the beta mu h cosine theta. So when we differentiate that, we'll bring down the factor of beta mu h sine theta. So we'd better, with the minus sign, so we'd better divide by 1 over minus beta mu h. And so now it's just, so now we can see it's a perfect derivative. And so then we get, just doing the integral, we're going to get 4 pi sine of beta mu h over beta mu h. And you can check that if you like. And so now we've calculated the partition function. So the thing that we actually want to measure is the magnetization in the z direction. How many spins are pointing along with the field? So an observable that one might want to know about would be the magnetization. In the z direction, the direction of the magnetic field. And so that magnetization I can define like this. The magnetization is then the sum over all the spins, and then the thermal average of the magnetic moment of the spin, its component in the z hat direction. So that's what it is. That's what we mean by the magnetization. And so that then I can write as the sum over the spins of mu cosine theta I, and that's inside a thermal expectation value. And so then I have to write that as the trace over theta of the sum I equals 1 to n mu cosine theta I. So that's the thing we're trying to take the expectation value of. Then our Boltzmann factor, e to the beta mu h sum over I cosine theta I. And then I have to divide by the partition function itself, which is the trace of e to the beta mu h cosine theta I with a sum. So that's what it is. And if you take one look at it, you'll say, well, wait, we can get this in a very simple way. Remember, I told you that when you do problems and you compute thermal expectation values in stat mech, you never do the integral. You always write it down as a derivative of the partition function. So we can see that this thing would come from differentiating the partition function. Because you can see here, I've got a mu cosine theta, and there's a mu cosine theta up here in the exponential. So if I were to then differentiate with respect to the external field, h, then that would bring down this factor from the exponential down to the ground floor. So I can write down mz, and you should check this, is equal to 1 over beta dz n by dh, and then divided by 1 over the partition function. And so that then I can write down as n times 1 over beta d by dh of log of z1. And I can do that because Zn is just Z1 to the n, and so that's a logarithmic derivative, and so that's where I get the factor of n. So the magnetization is proportional to how many spins there are, and then I just have to take the derivative of the log of the partition function with respect to h. And the partition function is calculated over here, so we just have to differentiate that. So let's go ahead and do that. So if I go ahead and do that, do the calculation, then what I get is that mz is equal to n times the magnitude of the dipole moments times coth of x minus 1 over x. And here x is defined to be beta mu h, in other words, mu h over kBt. And so you can see that this now shows you this energy versus entropy behavior that we talked about, because notice that when x is much less than 1, that means that kBt is much greater than mu h. And so the entropy is going to win over the internal energy that you get by aligning with the external magnetic field. And when x is much larger than 1, then the mu h is much greater than kBt. And so that means that the field is much stronger compared to the temperature. But it's not a case of saying, oh, well, something is high temperature or low temperature. That's not the case. That's not the point. When you say low or high temperature, you have to say with respect to what? And in this case, the energy that it's with respect to is mu times h. Okay, did you have a question, Andrew? No, okay, good. All right, so let me carry on then. So then we can calculate the behavior of the system at low and high temperatures by doing a asymptotic expansion. So for x is much less than 1, I can work out that cof x minus 1 over x has the following expansion. It's x over 3 minus x cubed over 45 plus dot, dot, dot. And when x is much greater than 1, then cof x is equal to 1 minus something of order e to the minus x. So if I were to draw the behavior that we're predicting, so let's draw that over here. So here is my variable that really is controlling the behavior. Here is mz over mu n. And then this is going to equal asymptote to 1. And then what we've discovered is that at high temperatures, it will asymptote to the value 1, and at low temperatures, it'll go linear like that. So if I ask what happens in the linear regime, so in the weak field, which means also high temperature regime, so that means x is much smaller than 1. So I can then just do this expansion over here. Then what happens is that the magnetization is then proportional to n times mu squared over 3 kBt times h. And so the magnetization is proportional to the strength of the external magnetic field. In this limit, of course, there's higher order terms. Let's write them as, say, order h squared or order h cubed. And this behavior is what we generally call in physics a linear response theory. And if I were to compute the isothermal susceptibility, so what is that? Well, that's just defined to be chi, fixed temperature, is defined to be the limit as h tends to 0 of dmz by dh. And then that is just n times mu squared over 3 kBt. And that inverse dependence on temperature is known as Curie's law. Okay, so that's very straightforward. And this function here, by the way, this function here is known as the Langevin function. It's a name that is sometimes given to it. All right, so that's the classical behavior, and one can work out heat capacity and all sorts of other things like that, but that is the way that one handles it. So now let's talk about the quantum theory, at least in outline. So in quantum mechanics, we're going to have to use, remember, the whole methodology of statistical mechanics is first you solve quantum mechanics or classical mechanics or whatever, then you do the statistical mechanics. So we now need to solve the quantum mechanics of a spin in a magnetic field. Okay, so I'm just going to quote for you the result from a quantum mechanics textbook. So what you would get is that you have a angular momentum, J, is equal to the orbital angular momentum plus the spin angular momentum. And the relationship between the magnetic moment and the total angular momentum. So let me just say, this is orbital, spin, and total. So the relationship between the magnetic moment and J, again, just comes from quantum mechanics. So this is mu is equal to G times E over 2 MC times J. And this G is the so-called Landé G factor, a very imaginative name. And this Landé G factor can be calculated to be 3/2 plus S plus 1 minus L plus 1 over 2J plus 1. And that's just atomic physics. And what we're going to be interested in is the Z component of magnetization. So that can be written down from quantum mechanics. So mu Z then is this G factor, E over 2mc, and then H bar M, and M is the magnetic quantum number, which goes from minus J all the way through to plus J. So that's that. And then we can then say that mu Z is then equal to G times mu B times M. And this mu B has a bizarre name. It's called the Bohr magneton. And mu B is this combination of fundamental constants, where m is the mass of the electron, and so that's what we get from quantum mechanics. All right, so then all we have to do now is work out the partition function. So we're going to just sum over the states, and the only thing that we really need to sum over is the magnetic quantum number. So I'm just going to put the result up, and we'll talk about it more next time. So we can do the sum over states. Because we're only looking in the Z direction, because that's where the magnetic field is. So we do the sum over states in the Z direction by summing over M. And so what that means is that the partition function for one spin is just this. It's the sum from M is equal to minus J to plus J, and then E to the beta, and then the external magnetic field times the mu Z, and mu Z is the Bohr magneton times times G times the times n. Yes, like that. And so the only thing we have to sum is, so beta h g mu b is just a number. M is the thing that we have to sum over. So this is then a very simple sum to do. And so next time, what I will do is next time we will evaluate. And then we will also check to derive the classical limit. Okay, so that's where I'm going to stop. It's 2:45, so I'm going to we're going to finish today's lecture here, and then we'll be carrying on as I've said in email with our next lecture and our makeup lectures. Okay, so let me turn off this.